Okay, so now, we're going to start with chapter 3, which, refers to the simple linear regression model. So remember, like in chapter 2 in the introduction, I already talked a little bit about the simple linear regression model. And basically, the idea here is that we only have one explanatory variable, and we're trying to relate our dependent variable or our outcome variable to just like a simple explanatory variable. Now, some of you might wonder, okay, so how realistic is this model? Well, in some cases it's very realistic. If you are designing an experiment, for example, where you are trying to measure the outcome, and you only have one factor that you have in your experiment. I don't know, for example, you have an experiment with cotton yield, and you have fertilizer, just nitrogen and different levels of fertilizer, and you design this experiment. Well, so that's a pretty good model because you only have one factor. Okay, so it's realistic in some cases. In some other cases, it's not very realistic, especially like in social sciences, where usually an outcome is determined by more than one factor. Okay. Now, however, the good thing about the simple linear regression model is that, as the name says, it is very simple. So we're going to try to understand pretty much all the details about the simple linear regression model, because by understanding the details of what's going on with the simple linear regression model, what's the mechanics, what's the interpretation, basically that provides us all the intuition and all the knowledge that we need to understand the multiple linear regression model. And the mathematics, actually, that it's used for estimation, etc., graphing, it's very simple and straightforward. On the other hand, the mathematics required to understand all the formulas that are used in the multiple linear regression model is more complicated, so we won't cover that. However, in terms of intuition, I think that everything that you really need, you can get it from the simple linear regression model. Okay? So let's start then with our simple linear regression model. So once again, remember this idea that we have, one way to think about regression is that, the value that you observe for the outcome has two components. One, that's the systematic component. Remember that corresponds to the average value of y. And then we also have the error term. So in this context, of course, we're assuming the deterministic component. We only have that one explanatory variable. Now, in terms of graphing, that relationship, we have y and x. So here, remember, if you remember back to your probably high school algebra class, basically, this model is nothing else, especially the model for the deterministic component is a model it corresponds to the formula for a line. Remember, that's just like a line. So that's what we have in the deterministic component. So in terms of graphing, we have y and we have x. And here, I just I chose upward sloping line. Of course, it could be also like a downward sloping line. And the formula for that line is given by beta naught plus beta 1x. Now, something to have in mind here, again, and I mentioned this before, but now I want to emphasize this thing. So here what we're doing is, if you think about this model, what we're assuming, if you see the graph and the formula, what we're assuming is a linear relationship between x and the average value of y. You see, that's what we have in regression analysis. Okay, so what we're assuming, again, is a linear relationship between x and the average value of y. We're not assuming a linear relationship between x and y. So the linear relationship that's assuming the model is between x and the average value of y. So here we're assuming a linear relationship between x and the average value of y. Okay, so it's important to have that in mind. Even though, when you are reading papers, or even when you are writing your own interpretations, you don't emphasize this relationship between x and the average value of y. I mean, that's kind of what's at the heart of regression analysis. Okay, so have that in mind. Okay, so that's important. And I mean, that's important as a general concept. That's usually what we do in statistics. And the typical example that I give is, again, in the context of medicine. You have these experiments where you have a medicine to treat certain illness. So usually what you have is you have a control group, and you have the group with the treatment. You give the medicine, and then what you do is you compare averages. Okay, so the conclusion is, if the medicine has effect, you find that on average, the group that received the treatment was better off than the group that did not, than the control group. So it's kind of the same thing here in regression analysis. Again, so what we're looking is the relationship between x and the average value of y. Okay, so, and now you're going to see how that is related to the way that we interpret our coefficients. Okay, so let's think about the way that we interpret both the slope, what's called the slope, and the intercept of this relationship. Okay, so given this idea, then how do we interpret beta naught, or the intercept? Anybody can help me? So what's beta naught of the intercept? No, well, independent. Yeah, well, that's one way to put it, but I want more. So you are saying that that's the value. Yeah, it's some sort of an independent effect. I don't know if I would call it. I cannot get your idea. You see, that's the value of y that is not related to x. That's kind of what you're, I guess, implying.
Is this where it crosses with y?
Okay, so yeah, the intercept is the value of, is the value, yeah, is the value of the value of y when x is equal to 0. Yes, but still, I mean, we're still not there. You're right, yeah, I mean, yeah, of course, the intercept is the point where the line is going to cross the y-axis. But in the context of regression, okay, I'm going to give you the interpretation. Okay, so you're exploring a little bit. So you see, in the context of regression, beta naught, the intercept, is the average value of y when x is equal to 0. Okay, which is the same thing. Okay, you see, it's the average value of y, because again, I'm going back to this interpretation of regression analysis, that it's not the same as a line. Because again, we have this random. And once again, the regression that we're estimating here is a regression, it's a relationship that relates the values of x to the average value of y. Okay, so given that definition, then the intercept is defined as the average value of y, or the expected value of y, when x is equal to 0. So the intercept is the average value of y when x is 0. Okay, so what about this law? Yeah, so graphically, and I guess before I move on, sorry, I'm going to digress a little bit. So graphically, yeah, so Anna was saying that that's the point where the line crosses the y-axis. So yeah, so that's what you were telling me graphically. And this is kind of like the definition using words. So now what about this law? Okay, so I'm going to give you the graph again. Okay, so sorry, okay.
Would it be the change in the average value of y when we change x?
Exactly. Okay. So, and again, so we're trying to emphasize that this line here that we're estimating is a relationship between x and the average value of y. So the slope represents the change in the average value of y when x changes by 1 unit. Okay. So graphically, here what we're saying is that if change, and so here I'm using delta x. Delta is change. So we're saying that if x changes by 1 unit, beta 1 y is going to be changing by beta 1 unit. So graphically, so this is what we have. This is what beta 1 is. Okay? So again, and this is at the heart of what we're doing with regression analysis. Sometimes we forget about it, but it's very important because this allows us to understand what's going on with regression. So you see, basically what we're building when we're doing regression analysis is a model for the mean average value of y. Okay? And again, this goes back to that. I always make this joke. That's why the statisticians are not very rich, because again, the things that that you can predict here are just related to the average value of y, okay, but not to the exact value of y, because you have this random component that is kind of hard to predict. Now, that being said, still, this is very important. Again, we're trying to make decisions. Another example that I use is, for example, pretty much everybody agrees that additional years of education have an effect on income, okay, on average. Okay, so everybody agrees with that. So you can go and run the regression, and you know that relationship holds. It's a relationship that holds in average. Because you see, in average, people that have higher levels of education are going to have higher income. So does that hold for every single individual? No, because you still are going to have people with low levels of education that are very entrepreneurial, that are very good at doing business, that might end up doing better than somebody who got lots of education. But still, we still recommend our kids, I recommend everybody, we all recommend our friends to go and try to get more education. Okay? Because we know that that's more likely to result in higher levels of income. But you cannot guarantee everybody to be better off than somebody who did not have education. Okay? So you see, so I'm not saying that this is not important. It's still, having that information is very important. And then again, here I have people in the field of nutrition. Such as today, I was reading about these papers where they look at the effect of drinking sugar beverages. So again, so we know that on average, if you don't drink that many sugar beverages, probably you're going to have a better health. But you cannot guarantee that outcome to everybody that stops drinking sugar beverages. Okay? Again, so I emphasize this concept a lot for now. Later on when we write interpretations or when you're writing papers, people tend to drop this interpretation regarding the average. But it's good that you have in mind. It's good that you have in mind that that's kind of what's going on here. And more generally, that's kind of what's going on with statistics and when you have experiments, etc. You're just comparing average values. But they still provide a lot of information.
So would you recommend to use, whenever we're writing a paper, to say on average?
It gets kind of boring, to be honest with you. It gets kind of boring. Okay? So once in a while, depending if you want to make a point, you can say on average. But it can get boring. So it's assumed that everybody understands that concept, but sometimes people forget about it. Okay? You are forgetting that this relationship is only a model basically for the average. So later on for interpretations, and usually even for exams, I don't penalize you because that's the way when I write papers. I don't use the average, except when I really want to make a certain point. Say that, you can say this relationship holds an average. However, maybe there might be a certain group for which this relationship does not hold, something like that. okay, depending on the point that you're trying to make. Okay, so now that hopefully you understand what's the interpretation, yes?
So when you say the average value of y, we're still talking about the outcome?
Yeah. Yeah, every time that I talk about y, this is the outcome or the dependent variable, okay?
Okay, so like for the intercept, that's the outcome when the independent.
So yeah, that's the average value of the outcome when x is 0.
X being the independent variable.
Yes. Yeah. So for now, I'm going to call just y and x, but remember I had defined those before.
Yeah.
X is the independent variable, and y is the outcome. Okay. Yeah. So for now, I will tend to use y and x. But every time that I mention an x, and I'm going to be consistent. That's an independent variable, an explanatory variable. And every time that I use y, that's going to be my dependent variable, my outcome. Okay, I'm never going to see. If you ever see me switching the names, you have a point in the midterm. I'm so sure about that. Okay? And that's kind of notation. Almost everybody uses y for the outcome and x for explanatory variable. But again, notation is notation. Okay? So that being said, notation is notation. As long as you define it within the context of a paper, you can decide to call x your dependent variable and y your explanatory variable. You're going to confuse everybody, but if you want to do that, and you can do, okay? Yeah, so I'll try to be consistent. So yeah, maybe here just to remind you, so remember y is the outcome and x is our explanatory variable. Yeah, if you are new to regression analysis, yeah, it's good that you remind yourself of that. Okay, so now we know, how to go about interpreting in general, especially the population model. So now let's see how is that we go about fitting the model. So remember, we have this population model that we believe that it exists. So this is the story. So we have this population model that we have in mind and that we want to estimate. Remember, the idea is that we go and collect some data. And we're gonna able to obtain this what we call the fitted line or the sample regression line. So this is the sample model. Okay, same. Do you remember, in chapter 1 when we're talking about population values and sample values? Here is the same thing. Before we had a population mean and a sample mean. Well, here we have a population model, a population line, and now we have this sample line. So it's the same thing. So just that you have very clear in your mind the difference between each component in the population model versus the sample model. I'm going to summarize them here. Remember, when we talk about the population, the average value of the outcome, we call it expected value of y. When we talk about the sample, we're going to use it y bar. When we talk about beta naught, which is the intercept, the population value is just beta naught. The sample value is going to be beta naught hat. For the slope, beta 1 in the population and beta 1 hat in the sample. For the errors too, the error is going to be just like an E, and it's going to be E hat for the sample. Okay, so remember, this is what we want to know. And this is what we will be able to know. Or this is what we will know. Okay, so we want to learn something about the population using sample values. So here we have the population counterparts and the sample counterparts that we will obtain once we use some data. Okay, and of course we go from the population to the sample by using some data, okay, in certain forms, which we're going to learn in this class. Okay, so let's see. Now, the procedure that is used to estimate this beta 0 hat and beta 1 hat is called the method of least squares. Okay, so I'm going to try to give you some intuition of what's going on with this method of least squares. So, to estimate the sample model, and and more specifically beta 0 hat and beta 1 hat. Although later on, we can estimate also the predicted errors, etc. But the main focus is in the coefficients. Once you have the coefficients, you have the line. And once you have the line, you can obtain everything else. So to estimate the sample model, we use what's called the least squares method. Least squares method. Okay, and I'm going to try to give you some intuition on how this thing works. Okay, so let's imagine that we have some data on both x and y. Okay, and the way that this data, is going to be given is by points. So if you think about that, like your Excel file, you're going to have something that's called y and x in a column, and then you're going to have values of x and y, and let's say that it's up to n values. Okay, so here to the right, you have the way that the data is going to look like. And here what I have is the graphic. Is the graph. Okay, so we have these pairs of values. Okay, now I'm going to wave my hands, and I'm going to say that we have a procedure to estimate that line. So of course, if your procedure is good, this this line is going to go through those points, kind of in the middle. So everybody agrees? And again, I'm trying to explain the procedure, the method. I haven't got there, so for now again, I'm waving my hand. So let's assume that we have a procedure, and we have this estimated line. So once we have that, we can write the sample model. Okay, so everybody agrees, understand what's going on. Okay, so now let's pick a specific value. Okay, and let's call it. So this is going to be the point that it's xi. This xi. We have a yi. Okay, so let's start with this thing. So yi xi is an observed point, so that's what you observe. So another way to say it is that yi is the observed value when x is equal to xi. Doesn't look nice. Let's see if I can save it. It says I cannot save this file. Let me see if I don't know why. The file is open. The file is written protected. terminology sometimes. Okay, so I'll give it. That works most of the time. Okay, yeah. Oops. Okay, so that looks better. Okay, so everybody's following? Well, now we have. That doesn't look nice. I don't know what's going on. That looks pretty bad. Okay, that looks better. Okay, everybody's following? So, we just pick a point. So this is the yi xi point. Now, the other thing is now we have a model. Okay. So you see, we can use our model to predict what's the average value of y when x is equal to xi. So if we were to use our model, that predicted value is going to be in the line. Okay? Everybody follows that. Okay, so now what we're saying is that using our sample line, we can predict yi hat. So that's going to be equal to beta of hat plus beta hat x. And of course, that predicted value is going to be here. It has to be in the line. Okay, so that's going to be our yi hat. Okay, so can you see the difference between the observed value for yi and the predicted value of yi? Everybody follows that. So we have an observed value and we have a predicted value. Okay, so now that we have an observed value and a predicted value, we can calculate the difference. How do you think that we call this difference? Just intuitively. It's the error. This is the error of the prediction. So the difference between what you observe and what you predict is the error of the prediction. Okay, so the residual or predicted error so Anna said error. So sometimes, again, with the language here it gets kind of tricky because the error is kind of the population error. So usually we tend to call it predicted error or residual. It's terminology. So good intuition, but sometimes terminology can be tricky. So of course the predicted error is the difference between what you observe and what you predict. Okay, so graphically that's going to be our predicted error. Okay, now of course we can do the same thing. We can go and calculate these predicted errors for all of the points. We could have picked another point. And just as an example, you see, let's say this would be the point xj. And this is yj. So this distance here. Oh, let me see, what is this? Oh, so this is supposed to be, so here this will be y j hat, and this should be the predicted error. Okay, and so on and so forth. Okay, so let's think about it. Again, I wave my hands. Well, but let's think just very intuitively. In an ideal world, okay, in an ideal world, what you would want all those errors to be? In an ideal world, you would like all those errors to be zero, because then you will have a model that is able to perfectly predict everything. Okay? That's the idea. And I'm going to write that down. Ideally, we want all the errors, all the predicted errors to be equal to 0. Okay? Everybody's following the logic. But now this question, is that even feasible though in this context? So remember, look at that cloud of points. So remember, two things going on here. You have that cloud of points, and you know that that population line is a line. So, can you fit a line that goes through all those points? It's not possible. Okay? So, we have to give up that, that ideal situation where all the errors are equal to 0. Okay? So, you have a lot of great mathematicians, statisticians that say, well, that's not possible. However, what we can try to do is to make the sum of the square errors, okay, the sum of the errors. So think about these errors here. And again, we're going to have, if we have n points, we're going to have n errors. They say what we could try to do is to make the sum of the square errors as small as possible. Now, some of you might be wondering, why are you using the square? So remember that some of these errors might be positive, like this one, like the AI, and some other errors might be negative, like the AJ hat error. Okay, so what you do with the squares, basically you are giving the same weight to values that are above or below. So by using that criteria, that sum of the square errors being as small as possible, basically you fit a line that is going to go through the middle of all of that crowd of points. Okay, so that's kind of what's going on, and that's what is the least squares procedure. So it's a procedure that allows you to estimate values of beta naught hat and beta 1 hat that are going to make the sum of these square errors as small as possible. Everybody follows the intuition behind it. That's kind of what's going on. So intuitively, it's very easy to understand. The math might be a little bit more complicated, but I'll talk about that in a second. So remember, ideally then, going back to the intuition, ideally we want all the errors to be equal to 0, but it's not possible if we want to fit a line. It is not possible if we want to fit a line. Okay. So remember, there is that cloud of points, so there is not a line that goes through all those points. So a good alternative is to try to make the sum of all square residuals as small as possible. As small as possible. Okay, so mathematically, so this is the sum of those square residuals, and again, so I've told you before that I'm not gonna be, sometimes when I do the sums, I'm not gonna add the I to the n. That's kind of assume that you understand that, but for now I'll do it. So remember, in the residuals, we said that is the difference between what you observe and what you predict. So you are trying to make that sum as small as possible. Okay? So everybody got intuition. So now let's look a little bit at the math. Again, I'm not gonna formally prove it. That's not necessary. But let's look how more or less the math works. Everybody get that? Okay, so that's some, first of all, kind of additional notation. You know, we call that sum of squares errors, sum square residuals, we call them SSE. Okay, so later on you will see even sometimes, I mean, when you see your output from software, they use this name, sum of square residuals, so they are referring to that. So once again, and I already mentioned that, so that's the sum of these square errors. Now, if you want to see it mathematically, we're going to plug in there the formula for y I hat, that is beta naught minus beta 1 xi square. Remember what I did here is I just plug in the formula for the predicted values of y. Okay, so everybody sees that. So this is the formula. Okay, so mathematically, this is what's going on. I mean, I know that some of you took calculus a while back. So what you do is you take the derivative of this function with respect to beta naught hat, and then with beta 1 hat, and then you solve. What? You make it equal to 0, and you solve for beta naught hat and beta 1 hat. And when you do that, I mean, you are going to end up with these two formulas that I have here. Okay, so again, mathematically, you solve for this thing, and that allows you to derive certain formulas for the slope and the intercept. And these formulas here are the ones that ensure you that this sum is as small as it can be. Okay, so there's not another formula that's going to make this sum as small as possible. That's kind of the mathematics. So the least squares method finds the values of beta naught and beta 1 hat that make SSE as small as possible. Again, I don't know yet. So maybe I need to restart my computer. Not right now, but okay, so using calculus, it can be shown that the formulas for beta naught hat and beta 1 hat are given by this, and I'm going to describe it a little bit more. So the slope, what we're going to do is we're going to have the products of the differences between the outcome and the explanatory variable, and then the denominator is going to be the sum of the square differences of each value of x and its average. And the intercept is just the average value of y minus the estimated slope times the average value of x. Okay? So we will see how to use this formula. The thing to get from this thing is that this, well, two things. One is that if you apply these formulas, SSE is going to be as small as possible. Okay? Because, again, the derivation of these formulas is based on this least square principle. And the other thing is that basically, and later on you will see, I mean, these formulas might look complicated, but basically the main idea here is that the calculation of beta 1 hat only involves values of x and values of y, which that's kind of what you have. I mean, I show you kind of in Excel, and now after this we're going to do an example. Okay, so basically the application of this least square principle in the context of the simple linear regression model, basically what you have to do is you have to apply this formula. As easy as it is. So we'll do an example by hand so that you will see how it works. Of course, in the real world, we'll be using software. We'll look at that later on, but it's good to do at least one example by hand so that you see what's the mechanics of the use of this formula. So any question, guys? So the other thing is kind of in terms of theory, to see if you remember. So let's think about the denominator, which I call SS, sum of squares of the x's. Okay. This SS here, by the way, every time that we see SS, that's sum of squares. So does the formula in the denominator remind you of something? Of the what? Yeah, if you see, that's kind of related to the formula of the variance of x. Remember, for the variance, we had divided by n minus 1. And we say that's kind of the average variability. So one way to think about the formula for the slope, you have the variance of x. And what about in the numerator? Does that remind you of something? I don't think that we talked about it in chapter 1, but it's a concept, a measure that you saw at some point. This is to measure the relationship between two variables. It's a covariance, okay, or the correlation. So this formula, so at the top is related to the covariance between x and y, or the correlation between x and y. The numerator and the denominator is related to the variance of x. Okay, so all these formulas again, you go back to those relationships. Okay, so and here I have different ways in which again, so we have this Sx. So Ss is sum of squares. So Ssxx is the sum of squares of x and x. And here I call it sum of squares of x and y to remind you that the formula involves x and y. Different ways to write the formula, but for our purposes, I mean, so you don't need to remember both formulas. There's different ways that you can write them and simplify. But I think the more intuitive ones are the ones that I provide first, because again, Ssxy is related to the covariance between x and y. And Ssxx is related to the variance. And that's kind of like the way to remember, more or less. The slope is given by the ratio of the covariance between x and y and the variance of x. Okay, so before we go to start an example, so the beta naught and beta 1 values that are obtained using least squares are called least square estimates. So you see, we're gonna be applying those formulas in the context of a specific data set. So we call those least squares estimates or estimated values. The corresponding equation is called the least squares line. Okay, so the values that you obtain with, and here I should say to emphasize, using least squares in a specific data set, okay, are called least square estimates, and the line is the least squares line. And the formulas that I just showed you above, the formulas for beta naught hat and beta 1 hat are called estimators. So these are called the least squares estimators. So you see the difference? The formulas are the estimators, and the values that you obtain are the estimates. Okay, so and this is good because when you are reading papers, when people are talking about estimator, they are talking about the formula, and the estimates are talking about the specific values. Okay, so the estimator is kind of the machine. I mean, so when I teach a regression line, and I have this very bad joke, I ask the students if they have seen the movie Terminator. So that's kind of the estimator. Remember, that's the machine. Okay? So this is the machine. That's the estimator. Okay? So, I mean, and most of the students have never probably seen I don't know, probably you have never seen the movie either. But that's kind of like a very old movie. So, estimator, terminator is the machine, is the formula. And the estimate is the specific value that you obtain when you apply that formula, that procedure. Okay, so I think we're done with the formulas. And basically what we're going to be doing for now is applying. So hopefully this doesn't look that hard. You're going to see that actually to apply these formulas is pretty easy. It's very straightforward. Okay? And actually doing it, I've told you, using a computer is even faster. I mean, once you have your data, it takes you 3 seconds. But we're going to go through the pain of doing it by hand at this one so that you see how things work. Okay, any question? Okay, so no questions is a good point to stop.